Alright, we continue with section 7. As I mentioned in the last video, if you have a graph that is a function that is whose graph is symmetric to the y-axis, we call that an even function. Now notice here that with an even function, f of the opposite of x is going to equal f of x. This is a test that you can use when you have the equation of the function. And again, symmetric to the y-axis. An odd function, as I mentioned before, was a function whose graph is symmetric to the origin, and in this case f of the opposite of x is equal to the opposite of f of x. Now I'm going to use these two down here to work and show whether or not, to determine whether or not these guys, m of x, n of x, and p of x are even or odd, or neither. But just based on the appearance, and I know this is based on my graphs, and hopefully you can follow my graphs here, do you see that this graph appears to be symmetric to the y-axis? So, of course, if it's in the textbook, it's going to be a much better graph, but based on its appearance, this is an even function. Whereas this has symmetry to the origin. And again, for every point, there's another point such that the line segment, the origin is the midpoint of that line segment. And you can see here that that's the case. Okay, well, make that a little bit bigger there. All right. And so this one is symmetric to the origin, so this is an odd function. Whereas in this case, you can see that this is neither symmetric to the y-axis or symmetric to the origin, so again, this one would be a neither. Now, of course, that's just based on appearance. If you're given the actual rule for the function, you can use these guys to test to see if you have even, odd, or neither. So let's try m of x here by plugging in the opposite of x. So m of the opposite of x means I have the opposite of x to the fifth power plus the opposite of x to the third power. So this is the opposite of, now the opposite of x times 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 the opposite of x is the opposite of x to the fifth. 5 negatives. And now the opposite of x times the opposite of x times the opposite of x would be the opposite of x to the third power. So the opposite of x to the fifth would be x to the fifth. And this would be minus x to the third. And you look at that and you say, well, that's not back to the original. No, but as you can see, these are opposites. This is equal to the opposite of x to the fifth plus x to the third power, or the opposite of m of x. So m of the opposite of x equals the opposite of m of x. This is an even function. Now let's try this guy over here, n of x. So I take n of the opposite of x. So that's the opposite of x squared minus the absolute value of the opposite of x plus 1. The opposite of x times the opposite of x is x squared minus the absolute value of the opposite of x is the absolute value of x, because they're opposites and the absolute values would be equal, plus 1. Well, this is right back to the original. So n of the opposite of x, oh my goodness gracious, nobody said anything to me. Good Lord, this is not an even function. This is saying the f of the opposite of x is equal to the opposite of x. This is an odd function. Where am I thinking? So hopefully you are saying, what's wrong with Mr. Turner today that he can't figure out that this is an odd function? This is an odd function. This guy here is an even function. Thinking ahead, and what I'm going to do next, and I can't keep track of what I'm doing and thinking ahead at the same time anymore. I'm getting too old. P of the opposite of x is equal to 2 times the absolute value of the opposite of x plus the opposite of x. So this is 2 times, of course that's the same as the absolute value of x, and this is minus x. Well, that's not the original, and if I factor out a negative, like I did in this example here, I get negative 2 times the absolute value of x plus x, and this is not the same thing, so it's not the opposite of the original or the opposite of p of x, so this one is a neither. Neither even nor odd. All right, now we leads us to a pretty important topic of piecewise defined functions, because certain functions, especially when related to applications, can't be determined by a single rule. They might have more than one rule. For example, if you're supposed to be home by 11 o'clock and you get home at 10:30, most likely your parents are going to be smiling. If you get home at 12:30, most likely your parents are going to be frowning or yelling at you because you went past what time you were supposed to be in. So in that case, the rule is a little bit different based on the domain. If it's before 11 o'clock, it's good. If it's after 11 o'clock, not so good. So a piecewise defined function is a function that's defined by more than one rule. It can be two or more. And each rule has a restricted domain. So like my really terrible example of coming in before 11 or after 11, that would have to do with the restricted domain. But here's one that's a little bit more mathematical. And we have a function that has three rules. And you can see how it's set up. Now again, in the old days we used to call these multi-ruled functions. Now they call them piecewise defined. It says evaluate the function for the given values of x. So you have to do this by plugging in, but you plug into the rule that it's defined for. So like the opposite, or excuse me, f of the -3 here, -3 would be in this guy, because -3 is less than -2. So this would be equal to -3 plus 7, this would be equal to 4. It's not difficult, you just have to make sure you plug it into the right rule. If I plug -2 in, I have to find the rule that it is defined for, it would be the middle one. So this would be equal to -2 squared, which of course is 4. That's coincidence. And then if I plug 1 in, 1 is not defined here, it's defined here. F of 1 would be just, well, it's a constant rule here, it's just 3. And f of 4, of course 4 is greater than 1, this would also be 3. That's not a coincidence, that's because of that rule, being the same one. Now, I want you to be able to graph multi-ruled functions or piecewise defined functions. Students have fits with this, and I really don't understand why. They want to graph every rule as if it was over its entire real set of real numbers, instead of just the restricted part of the domain. Yeah, I mean, if you want to picture it that way, that's fine, but you only want to graph where it is defined. So in this example, and I'm going to put both of these on here, I just used two different colors. Sorry about that, but I'm running out of space. I'll do this first one here in red. So I have a constant 2 for all values of x less than or equal to 1. So this would be the line y equals 2. Y equals 2 is a horizontal line, but we're only defining it up to 1. So it would look, including 1, so it would look like this. Notice the point being filled in there because of the equal to. Now in this part here, y equals -2x, that is a line that has slope -2, goes through the origin, but we're not going to go through the origin because we're only defining it greater than 1. So since 1 is the cutoff, even though it's not included, I need to know what's happening at 1, and if you plug 1 in, you're at -2. So at 1, -2, I'm not going to put a filled in dot, I'm going to put an open dot there, because it's not included. And again, I want for all values greater, so my slope is -2. That would be like down 2 to the right 1. And it would look like a line or a ray, kind of like that. And that would be the graph of this piecewise defined function. Now in this next example, I have g of x is equal to the absolute value of x, that's at v shape, for -4 less than or equal to x less than 2, and then equal to the line the opposite of x plus 4 for x greater than or equal to 2. So first things first, I'm going to get this part of my V shape here, starting with -4. Hope I have my graph big enough. It might go into the rule a little bit. -4, 1, 2, 3, 4. It does look like it's going to go into it a little bit. Filled in dot because of the equal to. It's going to go through the origin here, and then it's going to go up to 2, 2, but it's not going to include 2, 2 because of the fact that there's no equal to there. So it looks kind of like part of a V, like that. That's this first part. Now this would be the equation of a line with slope -1 and y-intercept at 0, 4, except they're only looking at values of x greater than or equal to 2. So again, I'll plug 2 in just to see what's going on here. And at 2, I have the opposite of 2, -2 plus 4, that's 2. So remember that open dot? Well, that's going to fill it right in, which is kind of cool. And then I am going to have a line with slope -1, so down to right 2 here, it would go like this. And I have the graph of this multi-ruled function. And as we're going to talk about in a little bit, because there's no breaks in this graph, there's no holes or gaps or skips, it's continuous where it's defined.